Hello students, we're going to try this problem. This problem is going to cover some important concepts in statistics, including the empirical rule, bell-shaped distributions slash normal distributions, the empirical rule as I'd mentioned, and also lastly comparing z-scores, a smashing little problem that I think illustrates some good concepts from the course. So this is about baseball and batting averages, and for those of you who are not familiar with baseball, the idea of a batting average is every time that a player is up to bat, the batting average represents the probability of, or really the proportion of times that they've made a hit. So you could think of it as a probability, like if I bat 300 or .300, that actually is 30%. That means 30% of the time I would make a hit and be on base, but we don't need to get into all the rules of baseball. Okay, so let's give this a shot. In 2010, the batting averages in Major League Baseball follow a normal or bell-shaped distribution with a mean of 0.258 and a standard deviation of 0.26. So we're going to answer these questions. Again, I do these as a try-along that you can try the problems yourself and then compare your results to what I get. So part A, what percent of players batted less than 0.58? What percent of players batted between 0.232 and 0.284? C, between which batting averages did the middle 95% of players bat? Typo. Play yours. And part D, what percent of players hit under 0.232? But wait, there's more. Part E, what percent of batters hit over .310? Part F, Carlos Gonzalez in 2010 hit .336. And what percent of batters did better than him at the time? That's pretty good. And then we can answer that question, part G, which percentile does that place Carlos Gonzalez in 2010? I'm going to follow this up with one last question here. This is an interesting problem. The next problem to this assignment is in 1910, batting averages also followed a bell-shaped distribution with the mean of 0.247 and a standard deviation of 0.034. So something to already note from our batting averages in 2010, the mean is actually going to be less, but it also has more standard deviation. So it's going to be hard to compare the two distributions directly, but we know how to do this, right? So in 1910, Ty Cobb hit .383 according to ESPN.com. And in 2010, the best hitter was John Hamilton, and he hit .359. Who did better relative to the year that they played? And we're going to support that answer using appropriate calculations. So who did better given the year that they hit? I think these are interesting questions because those of you who know baseball know that things change over time. There's different rules. The players have definitely gotten, I'm sure, faster, stronger, and all the above, more athletic, more competitive. People have got their strategies for playing down much better than 1910. So it's a good kind of question to see who did better relative to the time that they were playing. Okay, so again, the idea is that you pause and kind of work your way through this. So I'm going to get started here. All right, for all these questions involving the empirical rule, you could already see right off the bat bell-shaped distribution. So actually, let's go back to the problem and let's take some important pieces of information. Bell-shaped distribution. It gives us the mean and it gives us the standard deviation. So once we're given that, what we need to do, and we can see there's a lot of problems to this, and a lot of them involve what percent of players did this and that. So what we need to do is draw our bell curve. So we're going to start with the mean And again, I forgot what the mean was already. So the mean was 2.58, standard deviation of 0.26. So the mean was 2.58 and standard deviation 0.026. So we're going to start with our mean, and we're going to include 3 standard deviations to the right. That's going to be 1, 2, and 3. That's going to be 1 to the left, 2 to the left, and 3 to the right. So now we want to put in our values here. So our mean was 0.258. Going to have to get out my calculator so I don't embarrass myself here. If we add 1 standard deviation, that's going to give us 2.58 plus 0.026, 2.84, and then 3.10, and I can do these 3.6. And if I take away 1 standard deviation, I have 0.232. Take away 1 more standard deviation, I have 0.206, and then lastly take away 1 more standard deviation, and I have myself 0.180. The next part, we should really do this before we really start answering questions, and this is the stuff that we just have to remember. Yes, the empirical rule told us, okay, we have our 68% are within plus or 1 minus standard deviation, 95% are within 2 standard deviations, and 99.7% are within 3 standard deviations. But I gave you a little bit more, and I said, well, if 68% are between -1 and +1, that's going to leave 34% by symmetry in each sector here. And I'm sorry, I'm not going to write those as decimals, excuse me. Write them as percentages. And again, these are numbers that unfortunately you're just going to have to memorize. We have 13.5% here in that sector. This was 2.35, and this was 0.15%. And that, believe it or not, is a 1, even though it doesn't look very straight. So why is my handwriting so messy on this? Well, it's the stylist. I'm used to actually putting, when I write on paper, I'm actually used to putting my my hand down resting on the paper. I can't do that on the iPad because it's gonna think I'm kind of like double selecting, kind of like a double click. So it makes my handwriting a little messy. It's hard enough on a stylus, so excuse me. Okay, so once we got this drawing here, we should have everything we need to answer the questions that were given. Part A asks what % of players batted less than 2.58. Well, let's remember the mean was 2.58. By symmetry, half the players will score above the mean, half will go below the mean, so 50%. Didn't even need the bell curve for that one, did I? And you might even not need the bell curve for part B either. What % of players batted between 0.232 and 0.284? But let's use that bell curve here and go, okay, 0.232, that was 1 standard deviation to the left. 0.284, that was 1 standard deviation of the right. We learned that's our empirical rule, that's 68%. Next question, between which batting averages did the middle 95% of players bat? So just a little flip-flop here. In these questions, we were asking for the percentages. Now we're given for A and B, we were given a batting average, and we had to find a percentage. For part C, we're given a percentage, and we have to find, in this case, 2 batting averages, between which 2 batting average did the middle 95% of players bat. Well, again, knowing our empirical rule, that's going to say, hey, 95% are within plus or minus 2 standard deviations, so that's going to be this guy here, so that's plus 2 standard deviations from the mean, that's minus 2 standard deviations from the mean. So going back here, I can answer this question, part C. It's going to be between so I forgot the number already. 0.206 and 0.310. Okay, next question, part D. What percent of players hit under 0.232? So this is definitely now, these are the problems where I really need this bell curve, because this is where the bell curve is going to be a lot more helpful. So we're looking for what percentage of players bat under 0.232. So here's 0.232. We're looking for this region here. And I can do this because I have all those numbers written down. It was this was 0.15%, 0.235%, and then 13.5%. So I add all those together, and they add up to 16%. So that actually means that 16% of batters hit under 232. So the answer here is 16%, and these are the ones that, once I have that bell curve out, it really, really helps. Okay, part E, what percent of batters hit over 310? So let's go back to our bell curve, and it's same concept here. So I'm looking for 310, and I'm looking for everything greater than 310, so I'm looking for this tail here on the right. Well, that's going to be 0.235 plus 0.15%. That's going to add up to 2.5%. Oops, wrong way. So easy, even a PhD in mathematics, a PhD candidate in mathematics can do it 93% of the time. Yeah, 93% of the time, that's right. So 2.5%. All right, this is true. Carlos Gonzalez hit 336. He was second best in 2010. What percent of batters did better than him? Okay, I told you he was second best, but let's use the bell curve to find that out. So he hit 336. So we're looking now, what percentage did better than him at 336? Well, that's going to be the last tail on the right, just a mere 0.15%. Lastly, which percentile did Gonzalez hit in 2010? Well, the percentiles we said was the number of observations less, or the percent of observations less than that given value. Well, we just found here that only 0.15% of people did better than him. That actually means that 99.85, the remaining 100 minus 0.015% of players did worse than him, or that is, had a lower batting average than him. So so these bell curves actually, if you look at the whole area to the left of the curve, actually represent percentiles. So that is this whole region. Totally messing this poor little bell curve up. I've drone all over him. But that's actually going to place Carlos Gonzalez in the 99th percentile, since at least 99% of players did worse than him or had a lower batting average in this case. Okay, let's try this problem. Last one. An interesting problem. Again, in 1910, batting averages also followed a bell-shaped distribution with a mean of 0.247, smaller mean, greater standard deviation of 0.34, that is. So in 1910, Ty Cobb hit 0.838. Pretty impressive, right? In 2010, John Hamilton hit 0.359. Who did better relative to the year that they played? Support your answers with calculations, and again, we're using the values that we were given at the beginning of the problem. Okay, so again, before we even start a calculation, let's just like think this over here. So clearly Ty Cobb had a better batting average, right? 0.35, 0.383 compared to 0.359. But again, we have to be a little careful because we see that in the year, the standard deviation was different in 1910, and the mean was different. So yes, there was a lower mean, but the more standard deviations could actually mean more variance. Like, hey, a lot of players did hit better and worse. Like there was a lot more variance, a lot more spread, a lot more unpredictability, I guess, in 1910, and less variance in 2010 as the game kind of progresses. For those of you who ever studied economics, we call this a Nash equilibrium. Like all the everybody's strategies were as refined as they could possibly be, as is the case usually with Major League Baseball. It's going to get harder and harder because people figure out better ways to play the game. So who did better relative to their year? Here's what we're going to need to do. We're going to need to compare the z-scores. So we'll take the z-scores of each player, and the z-scores again represent the number of standard deviations from the mean. The more standard deviations you are from the mean, the more unusual the observation. Again, and this applies for distributions with similar shapes, and we were given both had a bell-shaped distribution. So let's start out with Hamilton, John Hamilton. So he shot, I'll call this Z John Hamilton. So he batted a 359. The mean for his day was I have to look back all the way at the beginning. 258 with a standard deviation of 26. 258 divided by 0.026. So we're going to find the z-score now for John Hamilton, and this is in 2010. So I'm crunching these numbers right now. I got a z-score of 3.88. Pretty impressive. That's 3.88 standard deviations above the mean. So now let's look at the z-score for Ty Cobb. Looks like a J, Ty Cobb. And it was given that he hit a 383. I forgot the mean of the day. I have to go back. And the mean in 1910 was 247. 0.247 that is. So if I calculate this z-score here, I got a smashing answer. Oops, that's not the right answer. Of, exactly 4. So what does that mean? The higher the z-score, the more unusual, which in this case is the better. Ty Cobb, you're the winner. Yay, 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 yay. So, so the answer would be, if this were a test, you would want to write down that Ty Cobb did better. And I say support your answers with appropriate calculations. So what do I want to see on your test? I want to see these calculations, the fact that you've calculated the z-score for each. And the answer is, again, who played better relative to that year? Well, it was Ty Cobb because he had a higher z-score, which means that he batted more standard deviations above the mean than John Hamilton did in 2010. All right, I hope that was a smashing example. The same kind of smashing, the way a baseball could smash a window, your neighbor's window. So be careful if you're going to go out and play baseball in the street, like I did when I grew up in Chicago. All right, ladies and gentlemen, thank you. Hope that was helpful.